Thank you for the introduction, Tom, and thank you for the invitation. I'm very excited to be here for sure. And I know I'm keeping you from lunch. I'll try to be brief. Those people who did look at the agenda will know I have an abstract that kind of says, it's got a lot of words, but basically through the morning you had a couple of key phrases, at least in terms of orienting you to what's coming now. I think Soren mentioned design for Six Sigma and similar methods. And the previous speaker just mentioned, in passing, kind of almost computer prototyping. So if you hold on to those two thoughts, that will kind of orient you to what's about to come. Okay, so what we're talking about here is essentially building surrogate models. So we have a system that's somewhat complex, but a system that we can simulate. And of course, the world is full of different simulation approaches, different simulation tools. It's very context specific in terms of what is it you're simulating and why. But the clear message is the earlier you can move these things into the product life cycle, the more potential benefit there is, so long as you can get it right, of course. When we talk about computer experiments, then we're talking about deterministic systems. And probably many of the people in the room will already be familiar with the idea of statistically designed experiments. Those people who have a Six Sigma background and similar will know that topic. The slight difference here, and it does have a lot of ramifications, is the fact that in deterministic systems, of course, there is no variation. So we're actually concerned with a slightly different problem. We're concerned with, we're concerned with bias. So basically, in a nutshell, rather than read all the words, we assume we have a system. Typically, it's highly dimensional in the sense we have a lot of inputs that we could mess with. We may have a lot of outputs too, but let's just keep it simple and suppose there's only one. We all believe that there is a real response function which is unknown, some kind of transfer function that maps the inputs to the output. And the challenge here is, with limited resources, can we build a surrogate model for that function, which would then allow us to do other things like robustness and so on. And the hidden assumption here is that this function is very expensive to evaluate, the real function. So if you think about large-scale simulations, in spite of hardware advances, then these things can take hours, sometimes days, just to get a single point. So if you can succeed in building a surrogate function, which is evaluated quickly, then there's a lot of potential benefit there. Okay, so that leads us on to the topic of what is known in the jargon about space-filling designs. So you have some kind of design space, some opportunity space, and these are the methods that people typically use to try and probe that factor space and figure out what's happening. And basically my example is, and I like to do things through simple examples, it's kind of a double-edged sword because it's simple in the sense that you'll get the concepts. It's also equally misleading because I already said typically these problems are highly dimensional, whereas the example I'm going to show is just in 3 dimensions actually. We're going to use fast flexible filling as a design strategy, and you'll see what that means in a moment. The reason we do the fast filling flexible designs is that for a couple of reasons. One is they can accommodate factors which are not continuous. And the other thing is actually they can accommodate constraints. And typically the factor space is constrained in one way or another. Okay, so let me show something in software. Excuse me. So basically, just want to introduce you to something that some people may know about, the Gaussian process. The Gaussian process is actually the form of modeling that we're going to use. It doesn't have to be this, but this is what we've chosen in this case. So let's cut to the chase here and look at some function. So in this case, the green function is the underlying function that we're trying to estimate. So that is the response function that we think, in this case, this itself is a simulation, so the true response is known. What's interesting, though, is how good the blue surface approximates the green surface. If I kind of move this around, you can see, even though the true response is kind of convoluted and wiggly, the blue does a very good job in estimating that in general terms. Now, I'm not going to tell you how I got this surface. That's the reason we have software, and given only a short time. I will point out, though, that was done with a relatively small number of runs. If you look here, the number of rows in the table there is quite small. Okay, so the Gaussian process is kind of a good way to estimate wiggly things in high dimensions. So here's the example then, as I promised, somewhat simple. If you want to make this a little more real, you could think of the fact that we're doing some kind of heat transfer, fluid dynamics kind of thing. Those codes typically take a long time to run. And let's suppose we want to do that in a cylinder, which of course we have x, y, z coordinates for the cylinder. And we measure our response, which may be, I don't know, viscosity or temperature or something. Well, obviously in software has a lot of common features, of course. If I come underneath this DOE menu, I'll find that there's a space filling design option here. I'm actually not going to do that. I will just click this button because it saves a bit of time. You can see that my response is there, and then I have X, Y, Z. But notice also down here, I have a constraint. And if you think about it for a little time, you'll realize that that is the constraint which makes this thing into a cylinder. You'll also see I talked about doing this with finite resources. Just because I had to choose a number, I said, let's imagine that we can evaluate this function only 26 times. Okay? And because I have a constraint, although there are these other space-filling designs available, then as soon as I impose a constraint, the only one that's left is this fast, flexible filling thing. Okay? So basically the problem now becomes, how can I pick those 26 points in such a way that I'm going to get a good surrogate function? Okay? So it's easily stated, at least. Here's a table now. And again, this is also a simulation. If you look at the surrogate function, you'll see it's somewhat simple function of x, y, and z. So I've got kind of some stuff happening in the xy plane and also some stuff happening in the vertical plane. Now, in reality, of course, you don't know that function. But just to give you an idea of what the method looks like, then I'm taking that as the real function. In reality, the challenge is, how do I estimate that function with a surrogate and do that in an efficient way using a small number of runs? Okay, well, if I had pressed the button to make the design, notice remember I asked for 26 runs, so there's 26 runs, okay, in this table. If I want to firstly check that I did obey the constraint, what you're seeing here is that where those points were chosen, and they appear to have been chosen somewhat at random, but at least they do obey the constraint to represent the cylinder. In fact, they're not, of course, chosen at random. There is an algorithm at work here, and that is the fast, flexible filling algorithm, which again I'll kind of gloss over. But the main thing is we've got a design that looks kind of interesting, okay? And of course, because we have a known function, we can calculate the response. Now the challenge is, how do I estimate this Gaussian thing, this Gaussian process? Well, again, it's easy. This is software makes this stuff easy. So if I come here, Gaussian process, I can take that to be my response, and I take these to be my x's. And I press the button, and I get an answer. Okay. And in fact, the answer I get is this one here. And again, given the time and given I don't want to keep you from lunch, I'm not attempting to explain what really happened there in terms of how this was constructed. But what I will do is show you the end result, which is this profile plot. So now we have our factors. In this case, we have a three-dimensional factor space representing position in the cylinder, and we have some response which is defined by the real function. Well, actually, in this case, this is the estimated function, the surrogate function. And with this profiler thing, I can move around and see things change and get an idea. Okay, so with 26 points, I've estimated this true function. Of course, in a few minutes, I'll address the question of how well did we actually do, because we know what the true function was in this case. But just to, well, let's look at what appears to be good news. If we run this script, we can look at actual versus predicted. That looks pretty good, right? In fact, it looks way too good, and we'll I'll explain why in a moment. But just to close the loop on the robust design thing, because that was mentioned in the abstract at least, let's suppose we actually believe the surrogate function that we just constructed. The next question might be, well, let's consider issues of sensitivity and robustness. And I just want to point out that we have a nice way to do that. This is, again, we can find a point in the three-dimensional factor space. We have a surrogate for the transfer function, but then we also have the capability to see how variation in the inputs will propagate through to variation in the outputs. So this is just nothing more than a Monte Carlo simulation. Once the function is known, then we can press the simulate button and we can see how well we do. And if we have, of course, spec limits on the response, we can look at levels of defects and so on. Okay, so that's just showing that we have that capability. If you read the slide, which you probably didn't, there are two competing ways to address this problem. One is to use an approach like I'm using here. Another approach is to use a regular grid of points. So just because to show the contrast here, if I look at the regular array of points, see how well that does. The first question is, where do I put those points? And that's non-trivial, but that's where I put them. So I basically have two sets of 13 points which are placed at two different planes in the cylinder. Okay, I can then play the same game. I can use for that design, I can then look at the Gaussian process, estimate the surrogate function, and then look at actual versus predicted, which also, guess what, looks amazingly good. Okay, so just to conclude, because this is a known function, which I showed you at the beginning, we can now do another simulation. We can say, okay, we estimated our surrogate function using 26 points, which admittedly is a small number, and I did that on purpose. Because it's a known function, you'll see we can estimate a lot more. Opened up the wrong table, excuse me. We can simulate a lot more data. So here you see we have 7,000 odd points. And let's look at this one, for instance. This one will show, again, the green is the actual response. The blue is what the surrogate function is, estimated by the Gaussian process. And here, of course, this is response plotted as a function of x and y. But here, by moving the slider, I can look at the z component too. Sorry, didn't quite do it right. This doesn't look quite so good as the one I showed you first of all, unfortunately. And that's because of the fact that I used a small number of design points in the space. We could improve that by doing, maybe 2 times 26. But what I was more interested in was not actually, in this case, building a good surrogate model, but just to make the contrast between the design that I've used and the regular grid thing. So let's look at this. This really is the punchline, and this should hopefully convince you as to why you should be interested in this approach. The blue one is actual versus predicted for this new set of data, and actual versus predicted for the fast-filling flexible design. The red is the one that you get if you attempt to use a grid design in this space. And remember, the main goal here is to avoid bias. And you can see the red results are clearly biased in a very almost catastrophic way. Neither of these is wonderful, I have to say. But certainly the blue one is better than the red one. And if you want to quantify that in terms of numbers, you could do so in terms of prediction errors. This is a little small, I'm afraid. But you can see here, this concept, this root mean square error, is just a way to quantify the difference between what you're predicting through the surrogate function and what you know you have, because in this case it was a simulation with a known function. And you can see again the space filling design did a lot better than the regular grid. Okay, so I warned you this example was simple in the sense that it shows you the mechanics, and maybe if you're interested in this topic, it pricks your curiosity to the point where we could talk a little more about it. I have just one more minute, and then I really do, honestly. I know I'm keeping you from lunch. I do want to say, for those people who know the topic, and there probably will be some, there's always variation in everything, and there's variation in the attendees here for sure. So for those people who do know the topic, I just want to point out that this design we're using uses a somewhat new way, a somewhat new algorithm to generate the design space. And why does that matter? Well, basically, this is kind of, this is the punchline there. Again, we have a constrained factor space, which happens to be the state of Georgia, just because we could. And what I'm comparing here is another class of space filling design, the blue points with the red points. The red points are the points that you get with this Max Pro criterion. And if you look just briefly at this, you'll see that what characterizes them is the fact the red points are further to the boundaries of the polygon. And that may seem like a simple difference, but remember, you're using these techniques in a highly dimensional situation. And as you increase the dimensionality of the problem, more of the volume that might be interesting is on the outside, as it were. So having an algorithm which reaches to the extreme of the factor space is an interesting idea. And as I say, somewhat new within the past couple of years. Oops. So I'm just going to show one slide and then you can get lunch.
Amazing number of punchlines on this.
I know, I'm sorry. That's the side effect of trying to do something which is... well, okay, let me say it in words. Hopefully, that was, for some of you, somewhat interesting. I'm very aware it's very different from what you've seen from the rest of the morning. This idea of computer experiments, building surrogate models, is a topic which clearly has a lot of value. We have customers doing this all the time in many different areas. So if you are interested in the topic, I'm going to be around for the rest of the day pretty much. So happy to talk some more. Thank you.
Thank you.
Thank you very much.